product of two vectors. The reason we do dot products is it's part of the process needed to calculate the angle between two vectors. Why you really want that, I have not come up with a nice applicable reason that's not for theoretical math people. Theoretical math people actually use this more often. Dot product can be, and we're going to use the dot product to determine if vectors are orthogonal, parallel, or neither. Now, we need to know what those terms mean. Do you want to find those out now, or do you want to hold off and wait until we actually get to finding out if things are orthogonal, parallel, or neither? Okay, let's do them now. Let's talk about what's parallel. Parallel. Two things are parallel when? So if they're lines, we refer to them as having the same slope. That's pretty close. They never intersect. That's also pretty close, not quite. There was one little thing you left out of that part, and yours. There's one more thing that everybody forgets. What?
They're not the same line?
No. That's not it. If I have a line up here and a line down here that never run into each other, are they parallel? This one's going this way and this one's going that way. Are those parallel? No. What are those called? Anybody know? Boy, your geometry teachers left out a little detail. They're called skew lines. The thing you have to add for parallelness and for the slope to be the same, to be enough, not running into each other, slope the same, they have to be in the same plane. So vectors are parallel if they're in the same plane and they don't run into each other. They would have the same slope, they would have the same direction, they would go almost the same direction, not quite. We'll get to actually what that's going to mean. What do you think orthogonal means? When we've talked about parallel in the past, okay, we haven't talked about it, but other people, you have. What was the other word that came up along with parallel usually? Perpendicular. Orthogonal and perpendicular essentially mean the same thing. Why we use orthogonal as opposed to perpendicular is, my guess is that because one vector can be over there and another vector can be over here, perpendicular things usually actually run into each other and form a right angle. What's happening with our vectors is you might have one over here, they never run into each other, but if they did, then they would form a right angle. And so I think that's the reason we use orthogonal as opposed to just saying flat out perpendicular. At least geometry-wise, we always make perpendicular things run into each other. And then, obviously, we can have things that are neither. They might run into each other. Well, they can run into each other but not make a right angle. Or, well, we're always in the plane, so we can't have skew vectors. So, let's look at our formulas. The formula that we normally use to calculate the dot product is the first one. Basically, if we have two vectors, a1i plus b1j is vector v, and vector w is a2i plus b2j, then the dot product is not a vector, but it's a number. And the number is gotten by multiplying a1 times a2 and adding what you get when you multiply b1 times b2. There will be no i's and j's. You will just spit out a number. Now you might be saying, okay, well, if there's such a nice, easy formula for dot product, why do we have the other one? Well, as I said, the main use for dot product is to be able to find the angle between two vectors. This other formula connects the angle between the vectors to the dot product. I believe it is this version of the formula that shows up on your final exam. So using that formula with a little rearranging and solving for theta, we can calculate the angle between two vectors. It comes out to be cosine inverse. Theta comes out to be cosine inverse of v dot w divided by the magnitude of v times the magnitude of w. calculate dot products and angles. Plus, one thing you need to know about this angle, all of you who keep forgetting that 2 pi part, best part, there's none of that in here. The angle between two vectors is the smallest non-negative angle. That means it can only be between 0 and 180, so when you take your cosine inverse, it's going to pop it out. There's none of this quadrant 3, quadrant 4 stuff. You're all going, oh, thank goodness. By the way, you'll notice that there's a big giant dot as opposed to a little one. The barely visible dot usually indicates multiplication. The big giant can't miss it dot indicates dot product. We don't ever actually multiply 2 vectors together, so that's if you're dealing with vectors and you see a dot between the 2 of them, notice we've never actually multiplied vectors together. We're not quite sure what that would mean. My last class was like, how would that look in the plane? And I'm going, I have no idea, because all we've got is i's and j's. We don't have any space for I squareds and j squareds. So, ready? We want to compute the dot product of each pair. Now we're going to start with the easy ones. Now, this doesn't look normal. Why do these look weird? These are shorthand for 2 vectors. Well, actually, it's I and I, so it's the shorthand for a single vector. What is the shorthand for in terms of vectors? The vector I is the same thing as what? What I plus something j? 1i plus 0j. We can just shorten it as I. So we're taking 1i plus 0j and we're dotting it with 1i plus 0j. So when we do our dot product, what do we get? Well, we'll get 1 times 1, so 1 times 1, plus 0 times 0, and that will be 1. So I dot I is going to be 1. Now what can you tell me about the 2 vectors I? How do they look? Where do they go? Which way do they point? 1i, 0j, which way are they pointing? That way, right? If I draw my thing, this is a unit vector that goes right there to 1. Yes? Everybody agree? So I and I are both that number. They're both going in the same direction. And that's going to be an important piece of information. Their dot product came out to be 1. Dot products which come out to be 1 can indicate that our vectors are the same vector or parallel vectors. What if we do I dot j? Well, what's j? J is shorthand for what?
0i.
0i plus 1j. Okay, so we're going to dot I with j. What will we get?
0.
1 times 0 plus 0 times 1, which turns out to be 0. Now, what can you tell me about I and j? How do they look? They look perpendicular. I goes to here. J goes to here. Okay, there's supposed to be both 1 and 1. There's my j, there's my I. Those 2 vectors are perpendicular. What do you notice about their dot product? It's 0. That's going to happen every time. No, they are flat. Well, I mean, these are flat out perpendicular because they run into each other. But 2 vectors whose dot product is 0 will end up being orthogonal because that even allows them not to run into each other, but be perpendicular if they did.